Alright, so the Wi-Fi is down, so instead I'm recording a video on caching and more specifically memoization in Python. So I'm going to use a pretty basic example. So for example, let's try to code how to calculate a Fibonacci number. So we define a function fib, which takes in the nth Fibonacci number. And this thing about Fibonacci numbers is that um, so let me just make a comment. Fib of n is equal to fib of n minus 1 plus fib of n minus 2. So the nth Fibonacci number is the n minus 1 Fibonacci number plus the n minus 2 Fibonacci number. And in our base case, we know that the Fibonacci numbers start with fib of 1 equaling 1, I think, and fib of 0 equaling 0, I think. Don't quote me on this one. So we can code in the base case. So this is going to be a recursive function. Recursion is a pretty basic concept. Just the main idea is that the function is defined with itself. So I'll just show you what it means and then explain it. So if n is equal to the integer 1, we will return 1. If n is equal to 0, we will return the integer 0. Now, so we don't really need an else here, because if any of these are true, then they will return. We will just return fib of n minus 1 plus fib of n minus 2. Now, with recursion, the point is you have a base case and you have your recursive case. So what will happen is, say we call fib of like fib 6. It will be like, oh shit, fib 6. Sorry, n isn't actually 1 or it's not 0, so we've got to go here. So it will call fib of 5, and also call fib of 4. But these are actually going to be done separately. It'll call this, and then it'll start going down. Down the tree, and then it will get the value for this, and then call this function. What I mean by tree is, I should probably explain this. Okay, no need to thank me for the flashbang, but basically, so we have like fib of 6, right? And then we call fib of 5. We find fib of 5, and we also have fib of 4. Then we find fib of 4 with this thing, and we have fib of 3 with this thing. This is just from the recursive definition, and we go all the way down until we get to fib of 1. And as you can see, even here, we're going to be calculating the same thing multiple times. We're going to be calculating fib of 4, and the branches coming off of this are going to be the same as the branches coming off of this. So if we implement caching, we can cut down a really large amount of computations being done, or more importantly, function calls, because in reality, function calls are actually not free, even though they may seem like they're free, because usually a function is like the computation done in a function is more expensive. Like if you have a function that does a lot of computation, it's kind of negligible, but if you call a bunch of functions which don't do like that much computation, it's not really negligible. So let me just show that this works. So like we can just loop 10, and we get the first 10 Fibonacci numbers. Print fib I, run, and we get 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. That seems about right. I mean, like I said, I have no Wi-Fi, so you can't really check. Okay. However, now let's try to get the first 100 Fibonacci numbers. Alright, so bad news, my headset died, so my microphone died as well. But good news is that now it's charged, but the Wi-Fi is still down. But we're back. So basically, if we try run this, the code calculating 100 Fibonacci numbers, as you can see, it gets quite slow and takes longer and longer each time. And I'm not too sure about the time complexity, and I can't really be asked to analyze it right now. But it's substantial. The time complexity, like, it's either a really high polynomial or it's exponential. I honestly don't remember, and I really can't be asked right now. So, one way we can cut this down is through something called, now what is the library called? Basically caching. And the way this is done in Python is quite nicely. We add the decorator LRE or to the, for example, the module which we import this from is from functools import LRE cache or just cache, yeah, just cache. I'm not quite sure what the difference is, but yeah. So, and you add this decorator thing, which basically means that if you input if you input the same parameters to this function and it's already calculated the output, it will just, instead of doing the function, it will just give you the output that it's already calculated and stored. So obviously this uses a bit more memory, but with this simple optimization we have computed 100 Fibonacci numbers in just like a millisecond, or I don't know how long that was, but yeah. And the way this works is pretty much it just chops down like these trees. Like it just goes down once, and then when it has to check for fib 4, it will just look it up. This does use more memory, however, for some cases this is very useful and a very easy technique. This is also sometimes called memoization in dynamic programming, which is where you solve problems using like subsets of those problems. So this is kind of a really basic example of dynamic programming because it's kind of like, well, what is fib of 6? Well, you can separate that into two smaller problems, which is fib of 5 and fib of 4. And then, well, you go back to the base case, which is more recursion, but yeah, I hope you understand what I mean. So yeah, thank you for watching, and maybe comment some other concepts that you would like me to explain or explore in some later videos.